Hi, in this video we'll talk about related rates. One of the key aspects to know about when to use related rates, for example, instead of taking the regular derivative, is when we have quantities changing over time. That's the key example. Let's say you have a different variable, not t, but a different variable, let's say x, p, q, r, instead, etc., etc. And we need to take derivative with respect to time. So notice how the variables do not match up. So far we've learned how to take the derivative as a function of x or other variables. So the notation, let's say f prime of x represents a derivative with respect to x, whatever that variable is. It could be t. So if you have t already, then you can just take the derivative as usual. But in this section, all quantities, variables, are functions of time, while they may not have that variable of t, time. So what we're trying to find out is the derivative, rate of change, with respect to t, but we don't have an explicit expression. A lot of times in real life situation, we do not. So let's say, for example, a function is f of x equals 5x squared, but we're trying to take a derivative with respect to t, time, a different variable. For example, if we knew the equation x in terms of t, let's say it was 1 plus 2t, then we'd have this function and we can use chain rule to find the derivative. So using chain rule, we as usual will multiply 2 by 5, we'll get 10 times 1 plus 2t times the derivative of the inside, which is 2. And then we can simplify it if we wanted to. But how do we do this implicitly without having an equation, which is what we're going to do next? For example, the notation that we're going to use, if x changes with respect to time, we'll have dx over dt. If y is changing with respect to time, we'll have dy over dt. Revenue is dr over dt. Area is dA over dt, and so on. So basically change of that variable over time. So let's say we're trying to take derivative of 5x squared with respect to time, t, but we do not have that expression. And again, in real life, that would be the case. So a lot of times we know the rate, it could be a number, but we don't know the actual equation. So how do we do it implicitly? Well, we would take derivative of 5x squared as usual, which would become 10x times, this is like chain rule, so this was the outside, times this is like a placeholder for the inside. Now we need to get back to t, so it would be derivative of x with respect to t, and that would be dx over dt. So essentially dx over dt is like the inside of the chain rule. That's basically what it is. So before, notice how it was 2 in our previous example, for our explicit example. But here we leave it as dx over dt, and we can substitute a number for it in many examples that we're going to do. So, and what we're going to have is a couple of the quantities that are going to be changing with time. That's why they're called related rates. For example, an area of a circle could be increasing and the radius of a circle could be increasing. And since area of a circle is a equals pi r squared, we'll see that very soon, then the area would increase and the radius would increase, and they both would be related. So the first few problems in that section, we're going to learn to translate the given information in terms of rates. So we'll be given some information. We're actually not going to solve anything till number 9, but we're going to be given some information. How can we translate it into variables or the rates like we have been? So for example, number 2 on that page, if there are presently 400 cases of Bangkok flu and the number is growing by 30 cases every month. So now note, we're given an amount and we're given a rate. Usually rate is very easy to discern as something is changing over time. So in class, I think we used x for number of cases, which you can do that, or you can use n to represent the number of cases. The variable doesn't matter as long as you're consistent. So let's say n equals 400 and the rate of change of n with respect to t, it's dn over dt equals to 30. And on the homework, you can just plug in, but this is, how you can represent information mathematically. And that's it. That's it for this example. So in the next example, we'll have a little bit more information. So the annual revenue of your tie-dye t-shirt operation is currently $7,000, but is decreasing by $700 each year. How fast are annual sales changing? So we're given an amount, revenue, and the rate of revenue with respect to time. And we need to find out quantity or sales, sometimes we refer to it as quantity, how they're changing. So how do we rewrite it mathematically? Well, as you can see, R will represent it with capital R for revenue equals to 7,000. dr over dt, rate of change of revenue with respect to time, is negative 700 because it was decreasing. And the quantity of sales, we'll call it Q for quantity, dq over dt equals to question mark. We do not know. We need a little bit more information. For example, revenue equals to price times quantity, but we need something more, maybe price, to be able to solve this question. But for now, we'll leave it. And here is another one that is going to come up. Sorry, let's get back to previous page. Quite a bit of time. So it's called the falling ladder example. It's an interesting example, but let's say we have an unstable ladder placed against the wall and it's sliding down, as you can see with the arrow. Eventually it's going to hit the ground, but it's also sliding away from the wall. So if you represent the horizontal distance with x, you'll notice how x would be increasing over time, and the vertical distance is y, and the y would be decreasing over time. So in this problem, we are given that the distance between the top of the ladder and the floor, I think that's the y, is decreasing at a rate of 3 feet per second. How fast is the base of the ladder receding from the wall? So how fast is x changing? So I think from reading the problem carefully, you can try to figure out which rate you're given, x or y, and solve for the other one. We still need a little more information. For example, how big the ladder is, and maybe one of the x or the y, and then we'll see how to solve it in a little bit. But for now, recall how we were given that the y was changing, the top of the ladder to the floor, dy over dt, equals to negative 3. Typically, dy over dt would be negative because y is decreasing. And we don't know what dx over dt is, but this is what we're looking for. Okay, so again, this is just the setup, but we'll see that actual problem in a little bit. And one more, where we're just setting this up. Stock prices are rising by 1,000 per year. How fast is the value of your portfolio increasing? So let's say P is a stock price, and maybe V is the value of portfolio. Then we know that, again, we're just given rate of change. So we'll write it as dp over dt. So get in the good habit of thinking, how can I represent the rate? How can I write it down? That is equal to 1,000 because it's increasing. And what is dv over dt? We do not know. And now let's solve some problems. Okay, so here's number 9. Sunspots. The area of a circular sunspot is growing at a rate of 1,200 kilometers squared per second. Incidentally, if the quantity is not given, let's keep in mind that area usually has square units, volume has cube units, and so on. And the regular distance, for example, for radius, would have regular units like kilometers, feet, etc. So, in that question, we're being asked how fast is the radius growing at the instant when it equals to 10,000 kilometers. So we can figure out the rate of change at a certain instant. At a different instant, it could be different. So it just depends at that instant of time. Which a lot of times with the derivative, we do the same thing. We can only look at it at a point. So first, let's translate all the information that we're given. And we will need a equals pi r squared to solve this problem in a little bit. But we know area is changing. So please write it as a rate at first. It's dA over dt equals to 1,200 kilometers squared per second. It's good to write it down. Now, what are we looking for? How fast the radius is growing. So we're looking for dr over dt when r equals to 10,000. So again, it's good to write it down. Well, you'll see why we need r, radius, just a little bit. So the area of a circle is a equals pi r squared. Now we need to take the derivative. We need to do this at some point of a equals pi r squared. We're going to do this implicitly. Notice there is no t somewhere in here, anywhere actually in the equation, but we will be taking derivative with respect to t. So keep in mind that's where we need related rates. So how do we do this? We take derivative of both sides. On the left hand side, you will have dA over dt. That's just derivative of any quantity. Derivative of a with respect to time would be dA over dt. Equals to, we'll keep pi as a constant because it is. So we'll just take it down like in a regular derivative. Then we'll take derivative of r squared like we regularly would. With chain rule 2, we would take derivative of the outside first, of the exponent first. So we're getting 2r times, now let's follow up with the derivative of the inside, so-called inside, which is dr over dt. So we need to follow up by the rate and bring it back to t. So derivative of whatever that variable is over the time. So again, derivative of r is the outside function, and that's 2r. And again, these quotation marks inside would be the rate of that variable over time. So I'll refer to it that way, but also sometimes I remember it as bringing it back to time. So make sure to follow up every expression by the rate. That's really the key for this section. Anyway, now we have enough information to plug in to be able to solve for the rate. So dr over dt is our variable. That's what we're looking for, even though it's written as a fraction, but we're looking for that rate. dA over dt, if you recall, that was 1200 equals to pi times 2 times 10,000 times dr dt. So note, we'll actually get 20,000 pi equals to 1200. So how you can solve for it? In a calculator, I recommend, let me pause it and actually write it out. So as you can see, you can actually write this out. This is how I put it in a calculator. 1200, you do not need parentheses for the top, but for the bottom, you do, because it's 20,000 times pi. Note, if you do not put parentheses around the bottom, you'll probably get a different answer than what we have. And you can find pi, I think it's second, and then the caret sign, I believe. You can search for it in your calculator. And so I'm getting 0.019 to the 3 decimal places. And the units would be, since it's radius, which is like length, it would be kilometers per second, because it's the rate of radius. And for B, we have a similar information. How fast is the radius growing at the instant when the sunspot has an area of 640,000 kilometers squared? So note, in this case, you're given area instead of radius. So, but how does this apply to us? So this is a similar situation. Again, we're given a instead of r. But the problem is when we took the derivative, which let me scroll back, notice we got dA over dt equals to pi times 2r times dr over dt. The r was left over from taking the derivative because it was higher exponent than the area, but area disappeared. We actually do not have area in the equation of the derivative. So it turns out that because you need radius, but you have the area, you may have to go back to the original equation. Sometimes you need to do this in every problem and solve for the remaining variable that you would need. For example, here you can plug in area and solve for the radius, because we will need that when we take the derivative. Which basically divide 640,000 by pi on the calculator, then take the square root of it. So I got about 451.3517. Actually, the more decimals you use, the more accurate your final answer would be. So you're welcome to use more decimals or use the answer key in your calculator. Now let's proceed with taking the derivative, which is same as above, and notice how we can now plug in the radius that we got before and solve for dr over dt that way. And I'm getting 0.4, I think it's 231 that I got on the homework. I'm not sure if there's a typo here, so you might want to double check, but it could be something similar to that. So double check with the answer. I think number 10 that we did in class was very similar, except the dr over dt, how radius was changing, was given. And you need to solve for dA over dt. It's a very similar problem in number 10, and I think the radius was given in part A and area was given in part B. But if you have dr over dt, then you don't even need to divide. You can just multiply everything out to find rate of change of area. So number 10 is a very similar problem. Now let's do a slightly different problem with volume, but it works very similarly. So a spherical party balloon is being inflated with helium pumped in at a rate of 3 cubic feet per minute. How fast is the radius growing at an instant when the radius has reached 1 foot? And we're hopefully provided the volume equation, so we can take the derivative. Again, let's do it of both sides. So derivative of v is rate of change of v with respect to time. So that's dv over dt, and that is given to us 3 feet cubed per minute. I think I jumped the ship a little bit. I didn't explain how I got that. So notice it doesn't actually say that the volume is changing, but because it's 3 cubic feet per minute, that kind of should give it away. Oh, it's the volume that's changing. So sometimes you just have to read it off the question. But we were given that, again, just by looking at the units. Then what is dr over dt? So it's similar to an area question. Now, how do we take the derivative? So we'll get dv over dt. Again, we can keep the 4/3 and pi as like a constant, or you can multiply it with a 3 when you put it down. Then let's take the derivative of r cubed. Again, let's deal with the exponent first. So it's 3r squared times, do not forget to multiply it by the rate at the end over time. So it's dr over dt. So we have two rates, dv over dt on the left and dr over dt on the right. And now, what did we have from the beginning of the problem? We were given that dv over dt was 3. That's our rate. And we're looking for dr over dt. Radius was 1. So it's actually 3 divided by 4 pi. Again, make sure put 4 pi in parentheses when you put in a calculator. And I'm getting about 0.24 to 2 decimal places. And it's feet per minute. So that's how we would do it with the volume. Now, here is a sliding ladders example, which we did earlier. So the base of a 50-foot ladder is being pulled away from a wall at a rate of 10 feet per second. Let's take a look at the picture as I'm explaining it. How fast is the top of the ladder sliding down the wall at the instant when the base of the ladder is 30 feet from the wall? So it sounds like a lot of information. Start drawing right away, okay? So what do we have so far? Let me actually put something in here. Notice how the ladder is 50 feet. So we can actually put 50 here. The ladder does not change with time. So this quantity, the hypotenuse, I guess, of the little triangle, we do not have. So we are given that, let's go back to the original problem. So how fast is the top of the ladder sliding down? So we're looking how the y is changing, right? So here's the top of the ladder, and it's dy over dt. Keep in mind, it's going to be a negative answer. Now, it's being pulled away from the wall at 10 feet per second. Let me scroll down a little bit. So we are actually given dx over dt, which is 10. And we're also given that at the instant when the base of the ladder is 30 feet from the wall. So here is the base, here is the wall. So we're actually being given the x. So what is the equation that would relate all these variables? If you recall from geometry, high school, maybe standardized tests, if you ever take, I don't know, GRE to go to graduate school or GMAT to go to business school. Anyway, one of those tests. But we're using Pythagorean theorem, basically. So it's x squared plus y squared, which are the two legs, equals to 50 squared. I purposefully left it as a constant because it's a ladder. We can plug in the x. We have to square it first. So it's 30 squared is 900 plus y squared equals to 2500, I believe. Then you can subtract 900 from both sides. And I think you get 1600. And take square root of that, you get 40. Okay. Now, see how we use the original equation to solve for one of the variables, just like we did with area to solve for radius earlier. Now, we need to take the derivative. Since we have two quantities here, x that's changing with respect to time and y, we're going to need to attach the rate to each one of them. Let's take a look what happens. So if you see, it's the derivative of x, which is 2x, times, follow it up with a rate, dx over dt, plus, now here's another variable, 2y times dy over dt. So here's our two rates that we need, equals to, now the derivative of the latter is 0 because it doesn't change over time. It stays the same. So derivative of constant is still 0. Now we can plug in everything that we've known from the problem. So notice you do need the x and the y and one of the rates to be able to solve the problem. So I think you get, I believe, 600 plus 80 dy over dt. So if you move 600 on the other side, you will get negative, which is why it's negative 600 divided by 80, and I think I'm getting 7.5. So negative 7.5 feet per second. So note, we can express this as the ladder is sliding down or decreasing from the wall at the rate of 7.5 feet per second. So here we can put it as a positive amount because we know it's sliding down. And last but not least, here is a business example, which you'll have a few more of those on the review, but definitely pay attention how we take the derivative here. So this one's number 15. Average cost function for the weekly manufacture of portable CD players. Remember those from, I guess, early 90s and or late 90s, depending on when you use them. Anyways, here we have the average cost example. 150,000 x to the negative 1 power plus 20 plus 0.0001 x dollars per player. And x is the number of CD players manufactured that each week. Weekly production is currently 3,000 players. Notice how it's quantity. N is increasing at a rate of 100 players per week. What is happening to average cost? So don't let the wording kind of confuse you. Notice weekly production, we're talking about players, so it's x. The rate of change of x with respect to time is dx over dt equals to 100. It's increasing. And we're trying to find dc bar for the average. What is it equal to? And here's how we take derivative of each side. Notice, again, take derivative of the outside times dx over dt for each piece, plus 20 happened to be 0, so we omitted it, plus 0.001. It's just a constant, but it's still times the rate. So regardless of what it is, unless it's 0, we multiply it by the rate. So I moved the x to the negative second power in denominator so it would be easier to plug in, and now we can just plug in. So I plugged in 3,000 in the denominator and 100 for dx over dt, and I think I got negative 1.66 on the calculator, and I believe we can interpret it. The average cost is decreasing by $1.66 per player, which is average cost, per week. So average cost is decreasing per week. And that's it for this section.